can either illuminate the scale. In this kind of light, it's really a little easier to see without the scale illuminated. Don't know how well you can see it from the back. This is a readout model, meaning I can turn on an on-screen display of the sensitivity and the speed of the time base. That's at 2 volts per centimeter, 5 milliseconds per division. Those reflect the current values. That's nice if you are operating the scope at arm's length and you can't see the knobs very well. You can see the on-screen display. It also is extremely handy if you're taking photographs, digital or otherwise, because when you have a display and you snap a picture of it, a screenshot, you also have the vertical and horizontal parameters saved along with it. That's been very useful in a lot of things. Tektronix pioneered that back in the, I believe it was late 60s, early 70s. Now, briefly about the actual units in this scope. This is a dual time base unit. It will actually show you a slow sweep alternated with a fast sweep. The left plug-in unit that's in there is a dual trace, meaning that I can switch in and have 2 traces from that one channel. I can also switch in and add a trace from the right side for a total of 3. You can put a dual trace plug-in here and have 4 traces. That's the main set of configurations for standard oscilloscope use. Let's see, I'm going to turn that off. I'm going to turn that back off. And you notice that the beam brightens a little bit when you cut the number of traces. That's because it's time sharing. This is not actually a dual beam, dual gun unit. When you select 2 traces, what it's actually doing is it is chopping between the 2. If you could trigger on that waveform, it would actually show you little dashes in the top trace and the bottom trace. That's good to know because if you are looking at extremely fast phenomena, you'll lose bits of your waveform in the chop times, which is why you have an alternate mode. As you step your time-based speed up really fast, the alternate mode takes away the disadvantage of the chop mode and gives you a smooth display without anything missing. And let's see, I want to put a waveform on here so you can see that. We're going to talk about exactly what it is displays. This is one of my favorite probes. It's a Tektronix E16. See which one this is. I think this is a 6062B. It is switchable either times 10 or times 100 from the probe tip. It has a grabber tip that goes with it. These are the cheapest one of these I have found on the internet was 1 cent. I felt bad because it was on eBay. The guy started his auction at 1 cent. I bid $10. It ended at 1 cent, and he had free shipping. I felt bad, so I sent him $20.
You paid $50.
Rip, but and he was a nice guy. When I sent him the $20, he sent me another bag of stuff. But let's see. These scopes, every Tektronix scope that I've ever seen in the lab grade has had a calibrator available on it, which is basically a square wave generator available right here. Now, I switch to times 1. Let's see, I'm going to direct coupling. I'm going to increase my sensitivity. Let's slow this down. And I don't know, I hope that display is big enough for everybody to be able to see to a degree. That's a basic sweep, repeating sweep that shows you, let's see here, that shows you the calibrator waveform. Now, what's happening is I have the trigger control adjusted for a stable display. If I knock it out of lock to where it can't trigger, the display just scrolls across. Once you lock it, it's said to be triggered or locked. What's happening is, on the first positive going part of the wave that it sees, it begins its sweep. That's me. The sweep continues until the time has elapsed, and this is 0.2 milliseconds per division. So every time you go a division, that's 0.2 milliseconds. All right, or 200 microseconds. So you're seeing a graph plotted. If you were literally plotting this on paper based on what you knew the signal was, it's the same thing. It is giving you a continuously updated graph of what's coming out of this connector right here. Now from that graph, if you put a meter on this, if it was an old analog meter, it would probably show you, 2.5, 3 volts or something like that. They're calibrated to read an average, and it wouldn't make a lot of sense. It wouldn't be accurate because it's not a steady voltage, it's not a sine wave, and it really wouldn't make much sense. That's why you drag out your oscilloscope. Looking at your scope, you see that I have a waveform here that is going, let's see, let me index it. So center is 0. It is going from alternating between 0 volts and plus 4 volts because we are looking at 2 volts per division vertical. So 2 up is 4 volts. Without a scope, you really couldn't possibly know that by looking at a meter. If you hooked a digital multimeter to that, I'm not sure what you'd see. The display would probably be erratic. It might stabilize or it might be erratic and not show any real stable value. That's why I like using a scope. I'll pull out an oscilloscope when a lot of people would pull out a meter. Because if you don't know what you're looking for, if you don't know what's in the circuit, this will tell you. So anyway, you are at 4 volts, you drop very quickly to 0, you're at 0 volts, you go back up to 4, and it repeats and refreshes as fast as the time base is set. Now, I can make the waveform look different by slowing down and speeding up the time base, but the waveform is still the same thing, we're just looking at it in a different manner. Now,
You can just see how clean power is, because like on a sine wave,
exactly.
if you're having problems in the house with your TV or something like that, you want to look and see what the sine wave is, see how dirty it is, and then you have to figure out what's causing it to be dirty. Now, this is where the perfect example of seeing the dirty sine wave or anything else like that.
That's an extremely good point, and that is one reason to pull out a scope. A case in point that affects ham radio operators. Years ago, many years ago, I was about 14, I think, and I was listening to Radio Australia or somebody one night, and all of a sudden, I'm not hearing it, I'm hearing rang, terrible hash, and it just started. So I thought, okay, this is something in the house. It's the power line. So I grabbed a scope, hooked it up to the power line, and on top of the sine wave, I would see literally. Let me see here. I can show you a rough sine. It's not going to show you very well. I thought maybe I could just pick up some hum. It's pretty quiet in here. But anyway, you had a sine wave, but you had this tremendous peak. A spike, we call it, a switching waveform on the sine. Then the sine wave continued to go up and over, and I saw another peak just like it. And it repeated. It was in perfect synchronization with the sine wave. Well, what did that tell me? It told me that somewhere in the house somebody had turned on a light dimmer because it was switching. There were triacs in that light dimmer, and every time the sine wave approached the same point, it switched on the bulb, and every time it delivered as much power as it was supposed to, it switched it back off again. So I started going through the house, found out the dining room light was on. Went down there, turned it off, the spike disappeared, and here was Radio Australia again. The oscilloscope was the tool that told me instantly what was going on, and the way it told me what was going on was the signature of the waveform. That's an extremely important concept because that's what the experience you gain, the time you spend with a scope will give you the ability to do. If you see, if I had hooked up to the IF in the radio and seen the hash, I would have recognized it there. You're looking for a sine wave, as he said. You recognize what the sine wave looks like, you'll recognize distortion. If you are looking at a triangle waveform that's in a sweep generator or a function generator, you can spot truncation, flattened tops and bottoms. That also comes up in looking at your signal on the air. I'm going to hook up a small transceiver in a second, show you an RF waveform. If you take, let me show you this little device is very useful for a ham shack. That's made by Bird. It's a signal pickoff. Basically, you put this in your transmission line going from your radio to the tuner, or the tuner to the antenna. Probably from the radio to the tuner is the best place to do it. It's adjustable. You can choose how much RF is picked off at this connector, and then you can lock it down. Basically, your signal goes through this device to your antenna or your dummy load, and the signal comes off here that you take to your scope. And by monitoring that, if you are running CW, you can see your keying waveform. You can see if the rise and fall times are right, or if they're too fast or slow. You can see if your signal is going to be mushy to listen to. You can see if you have key clicks. All that just from the display of the scope. If you're running single sideband, you can run test tones. You can run sine waves. You can tell from a sine wave if you've got distortion. You can run a trapezoid waveform. If you're flat topping, you'll see it there. It's not a bad way to peak tune your amplifier. Run the right waveform through, peak it while looking at a scope, then you know what you've got. A lot of people will use some folks use a pulse tuner to tune up a rig or tune up an amplifier. A nice adjunct to that is to have a scope to watch the pulses. You can see them on a peak reading watt meter, but if you're looking at them on a scope, think of that as a meter with virtually zero response time. So you see exactly what's happening. Let's see. And it's still basically plotting time in the horizontal plane, in the horizontal axis, versus amplitude in the vertical. Does anybody have a question? I'm running through this kind of quickly.
A lot of times, I know we pick up interference with these fluorescent lights.
Oh, yeah.
And the only way to find that is with an oscilloscope.
Exactly.
The fluorescent lights are really, really bad on some pieces of equipment, but of course, over a period of time, we've gotten better equipment to eliminate that. But
yeah, but it's true.
Yeah,
it's true.
Today, it still works.
And because a fluorescent's got the ballast in it, it's an inductive load, and they can generate terrible hash if you've got a compromised bulb or a compromised ballast or anything like that.
You might have to change the light out in your camera, like that. To get
exactly. I know in my old shack, I had to always run with the fluorescent lights off because they generated a bunch of hash. That's true. That's true. So in a ham shack, a good scope is literally handy, almost essential for so many purposes. Now, a nice thing about a convertible mainframe like these, and this particular one, the 7603, is available very inexpensively from eBay, various sellers. I got this one literally as a throw-in with a spectrum analyzer plug-in that I bought because I wanted the plug-in. The only damage to it was that the guy hadn't packed it well, it had been bashed on the back end, so just today I finished doing the sheet metal work, got the back cover on, put it all back together to work, thank the Lord. But anyway, if you have the room and are interested in developing a deeper knowledge of oscilloscope operation, I recommend a lab scope. Doesn't take up a lot of bench space. I keep one very similar to this on my workbench all the time for quick and easy use. The beauty of it is, as she's set up right now, that's fine for watching your waveform, basic troubleshooting, looking at interference, fixing things. But You could literally swap out these two plug-in units for a spectrum analyzer and be able to look at your signal purity, harmonic content, all that sort of thing. You can swap out these two units for a 7S12, which is a time-domain reflectometer plug-in, which is basically this instrument in a small plug-in module to convert that. And in the same mainframe, by choosing which modules you install, you can do any of that sort of stuff. Spectrum analyzer, whatever. This mainframe could look at a 14 gigahertz signal by putting the right sampling plugins in it. It's all that. Anyway, and I think right now we're at the bottom of the price curve on a lot of this stuff. It's just gotten cheaper and cheaper, and I don't see how it's going to get any cheaper. Yes?
Now, as I ask this question, remember that I'm a little large man. If you use one of these things, like I want to look at my amplifier and make sure I'm not splattering.
Which is
hear a lot of
great, yeah.
So can I do that with the oscilloscope, or would you need the spectrum analyzer plug-in module to do that?
You don't need the spectrum analyzer plug-in. The place that comes in really handy is, let's just say you had homebrewed a transmitter and you wanted to see if it met purity, signal purity requirements, which is basically harmonic radiation. You stick your spectrum analyzer in, and it's just an easy way to do it. And key her up on 40 meters and then look on 20 and all that, and look at your harmonics, and it just gives you a nice graphic display. You could say sweep from 7 to 40 megahertz all at the same time, and your harmonics will appear as calibrated bumps up there. It's a convenience. You could do the same thing with other methods. But for looking at your signal and tuning your amplifier and making sure your linearity is good, a standard rig just like this would be excellent. Or,
so what would I look for on the screen? It's properly tuned and not splat.
okay. Basically, what you'd want to do, depends on how you tune. If you tune, if you use a pulsar to tune, like a lot of folks do, what you would do is I would recommend would be to tune it up as you normally do, looking at your power output as you peak the plate and load controls, and then as you look at the scope, touch up the peaks again. Then as you start to speak, watch the scope as you start to speak, and if you're flat topping, you'll see odd, truncated, compressed peaks on your signal, whereas while you're talking, you can literally touch up the loading control again, and as you see those peaks going up and not flat top, that's the best way to do it. I like doing that over test signals, because if you're running test signals in it and you flip over and you're on the mic, how do you know your level coming off the mic's the same thing you were sending in as a test signal? The test signals I find more useful when you're troubleshooting equipment. For a normal tune-up, I like to tune it up and then flip the scope on and watch it as you speak, because you'll see it. Interestingly enough, now it's been some years, and this directly addresses that, it's been some years, but in the late 70s when I was a broadcast engineer, got to figure we had some digital test gear at the station, we didn't have much. The modulation monitor that we had on the AM WJDX was an analog meter, it was a needle. Now, it had an accelerator circuit, a peak reading circuit, and all this stuff in it, including overmod lights and all that, to hopefully be accurate. But I had an old tube type scope mounted in the rack at the transmitter building, and I could catch overmods on that scope that the monitor missed. So my final knowledge of modulation on that broadcast station was looking at a scope under normal program material. And if I wasn't seeing them there, then they weren't happening. Now, does that answer your question, Mike? But now, as far as what scope to use, depends on how versatile you want it to be. Lab scope is the peak of versatility. You can even buy a 7800 or 7900 mainframe that is 4 plug-ins wide, has storage and Lord only knows what other features. The amazing thing is you can buy that scope for $250. It went out of the catalog, and a 7834 went out of the catalog in the 80s for probably $25,000, $28,000, I'm guessing. I'd have to look. But I bought mine for $250, and I bought another one for a junker for $150. So that's what you get. But Mike, what I was going to tell you, if you just want a basic unit to check your modulation, basic troubleshooting, general use, something like this. This is a 2215. It's a later scope. This one, I'm going to say these were made in the early, mid, and late 80s. This is a 60 megahertz bandpass. There's a similar model for a little more money that's 100. I think I paid $75 for that one. You can find these on eBay all the time for under $200, and most of them working and in calibration. They're easy to fix. The parts are still available, and that's the bargain. You can take that scope and be perfect for looking at your amp, watching it tuned up. The screen is resistant to burning. It's dual trace. Yeah. So that's what you'd spend, and that would be fine. You can get nice carts that these fit on. I've probably seen them various places. 2 big wheels, 2 small wheels, tray on the bottom, a single shaft comes up, and about here you've got a tilt top tray. Those are available everywhere, and it makes a nice roll-around accessory for your shaft. Anyway, that's for watching your signal whether you're running barefooted on an old tube type rig that you have to tune and load, or whether you're running an amp. I'm trying to think. You actually could, if you wanted to do it, you could watch multiple places, but that's probably the best way to do that. The Kenwood station monitor, the Heath kit, I forget the model number, station monitor, all those are basically simplifications of this. They're doing the very same thing. This just gives you a lot more control and a lot more versatility. Let's see. All right, I want to key up an RF wave. I want to show you that monitor.
Some of the differences on some of those scopes is the speed that they scan at, and for our purposes, most of these scopes, the speed's fine. But on certain applications, you have to have a scope that has the proper speed for what you're looking at. But our applications are, these are fine. But
exactly.
But some people don't realize the speed makes a big difference on your application.
You just gave me a great opportunity to put in a plug for analog scopes. Thank you very much. Well, as you can see, all of these are analog instruments. That's what I like, and I'm fixing to tell you why. 2 reasons. One is all these analog instruments use what I call classic control set. It's the same type of controls that have been on oscilloscopes since the 40s. Time-based speed, vertical sensitivity, all that sort of stuff. But the big deal is, with all these analog scopes, signal comes in, signal goes through an amplifier, it comes out of the amplifier, it goes to plates on the CRT. There's no processing, conditioning, or anything. Literally, within the bandwidth of the scope, the signal is displayed exactly as it comes in, and you judge what it is. You see what's really there. Now, with every digital scope, they may call it real-time digital, they may call it sampling, they may call it a lot of different things, but with every one of them, the oscilloscope is looking at the signal, deciding what's there, then generating a display to show you what it thinks is there. Now, as long as it's right, that's all fine. But there's a problem called aliasing. And here's what happens. Best way to explain it. In this scope, as long as the signal I'm feeding it is below 100 megahertz, not only is the waveform going to be accurate, its calibration is going to be accurate. I can go above the bandwidth of the scope. The signal will slowly fade away, but the waveform will always be accurate until it fades from view. If I take a 100 megahertz digital scope, even if it's called real-time digital scope, if I've got the time base set too slow for the signal that's being fed in, rather than just a shaded bar signals that don't really mean anything, it may generate a waveform that doesn't look anything like what's really there. But it's going to show you because it thinks that's what's there. And they'll fool you. Every one of them
That's
will
where
fool
people
you.
get in trouble with.
Do what?
That's where people get in trouble.
It is. And you're looking at this, it's showing you a high quality waveform, but it bears no resemblance to what's really there. So you almost have to be sharper to watch out for that than to use an old analog scope.
So when you look at these schematics, you need to see what the waveform should be at that point.
Exactly.
Otherwise, you don't know what to look for.
Well, and the problem is, a lot of times when you're doing troubleshooting, and sorry to jump subjects, but if you're troubleshooting and the instrument you're troubleshooting is defective, you don't know what waveform's there. So you've hooked your scope up to find out. So I just always feel a little better knowing that I'm making the judgment instead of a microprocessor and the scope making the judgment. Anyway, okay, but let me fire up this little radio. Problem SGC 2020. I need to get some power. There you go. There's your actual RF waveform. And that is 200 nanoseconds per division horizontal, 200 millivolts vertical. And by adjusting, let's see, that little signal pickoff, as you can see, you can adjust that to whatever sensitivity you want. Speed your time base up, slow it down. Now that's actually looking at the RF waveform. You'd be down in there looking at the actual audio waveform. This is the cool thing though about the analog scope. That's what's really there. If I slow the time base way down to here, if I was a digital scope, no telling what it would show. But when I look at that, once again, that's the thing about learning the signature of a waveform. When I look at that, I say, okay, my time base is too slow. There's something there, but I'm not seeing it. So I start running it out faster. There we are. Let's see. Anyway, that indicates why you're really safer doing troubleshooting with an analog scope. And it shows you that this scope is plenty fast to look at anything that's going to come out of an HF transmitter. I'm up on a little bit, well, that was on 1.8. Let me run up to a little higher band. Go back up to 20 meters. Let's go. Same deal, except now I need to run the time base out faster. Same waveform, we're 50 nanoseconds per division at this point. There's 100 nanoseconds per division. Now, the interesting facet of that is, let's see, I'm going to rock this back and forth and I'm going to say, all right, I'm seeing about 50, let's see. I'm seeing 50, 60, I'm seeing 70 nanoseconds as the period of that wave. I'm not running calibration on these scopes. I can't say for sure how accurate that is. Let me just do a quick calculation on that. Find my calculator. Okay, just reading off the face of the scope, 70 nanoseconds inverted gives me 14.285 megahertz. So, right from the scope, without, like I said, without even having it carefully calibrated, I can tell the approximate frequency of the signal, I can tell the amplitude of the signal, I can tell the apparent amount of distortion or purity in the signal, if there are defects, if there was ringing, if there's distortion. For that matter, if there was heavy harmonic content, we'd see it as a distorted sine wave. So from the one single display, you see all that. From a meter, you don't. Another nice thing about monitoring, as Mike said, another nice thing about monitoring your signal with a scope is that it's the best way in the world to see instantaneous power. If you want to know really, truly, and accurately what your amp will do, is load it up into a nice 50 ohm dummy load, put a scope on it, Load her up, and look for your max peak. Then just back the calculation out, and you know beyond any shadow of a doubt what it does, and you're not worried about calibration of a meter or anything else like that. So in seeing if your tubes are good, for that matter, an old tube type rig, if you're running a Collins S line and want to know, okay, are my finals doing it? Well, load her up, put the scope on it, and see exactly what it'll put out in PEP, truly, because the response time of the scope display is literally virtually nothing, in that opinion. Does anybody have a question before I move to something else? All right, I want to show you a special purpose instrument. Let's see. This is a small time delay reflectometer. It is the last word in cable analysis. This instrument is funny. This displays probably the only place I've ever run into, being a Tektronix fan, where circuit design wise I think, why did they do this? On a handful of instruments, they designed them so that the NICAD pack is part of the power supply. You have to have good NICADs or the instrument won't run. Well, I didn't like that. So I built a circuit that emulates NICADs that allows me to run the instrument straight off AC, but a quirk of it is I have to turn the power on, let it charge a big capacitor, turn it off. Now when I turn it back on, she'll come up. And this is a small display, and I'm sorry about that, but what this unit is an extremely fast oscilloscope, probably with a bandwidth of 10,000 megahertz, something like that. But it also has an extremely fast rise pulse generator in it, probably 25 picosecond rise time, something like that. What this unit will do, it sends that pulse down cable and watches what comes back. And from that, you actually see what's going on at all points down the cable, including at the other end. Now, let me grab a couple of test loads over here. This is one of the most useful things you can have in a shack as well. These units, I see these on eBay, in the $150 to $250 range. The little known fact is, all that's wrong with most of them that are listed as non-functional is bad NICADs. Let's see. All right. Now, I'm going to hook up about a slightly over 5-foot cable. And what you see, and I'm sorry the display is not there, what you see is called the step pulse. Basically, right at this first division, that right there is that's the front panel. All right. I am calibrated so that first division is the front panel. Now, this cable is a little over 5 feet long. So when I look at it, probably 5 feet 2 inches. That horizontal portion of the trace right here represents 50 ohms. Although you're looking at reflection coefficient, essentially, if the cable goes to a short, which I'll show you, if the cable goes to a short, it's going to go down to nothing. It's almost like looking at an ohm display. And there's the end of the cable right there. If it goes open, it goes high. If you have a matched load, 50 ohm load, it stays flat. Now the interesting thing is, if you look at it, I'm going to drop this down so that you can see. You expand that, and this is very small. You can actually see the connectors. These jagged lines here and these jagged lines there are the impedance variation as you go through the connectors. And you can see when I pull it off. And this anomaly here, you can see, the impedance goes slightly down, slightly up. Those are imperfections in the cable. Now, if I go out here and add another cable, it just makes the display continue. But as you can see, there's still a connector there. But if I scroll on out, there's the end of the cable again. I put a load on it, grab another adapter. And this is all fine to play with when you've got 5 feet of cable. But if you've got 1,000 feet of cable or 175 feet of cable, then it gets really convenient. And drop my load here. Once again, it goes back flat. I'll give you an interesting example of where this really did save us a lot of time. At the Rankin, at the state EOC, there was an experimental antenna installed that they were having trouble with. They couldn't get it to tune. It was as if there was a problem in the transmission line. So I took this particular instrument out there, hooked it up, and what I saw, I wish I still had a picture of it. You could see, 80, 90 feet, I want to say, out the cable. It looked good. Then it wasn't a square wave, it was a rounded step up. Well, what that told me was that there was a loss of DC connectivity, but there was a capacitive connection across it. And there was a defect 70, 80 feet out, and it showed us to the foot where it was. So they hired some guys to come in, crawl down under the foundation, get in there, and there's where it found. Bad connector. So they pulled some new cables in and solved the problem. Similar situation down at radio station, down at Mix 96's transmitter. Several years ago, they had a burnout on the 100,000 watt broadcast rig down there. They had to take the antenna down. They took some of the transmission line down, and y'all probably know George Thomas. He was the chief engineer there at the time, and they didn't know if they had all the burned out transmission line down or not. And I think they had 1,100 feet of it still on the tower, and he had a dummy load put on the top. So I didn't have this unit at the time, but I had a big old tube-type mainframe this big, same sort of deal though. By the time it came to the reflectometer. And we took it down there, hooked it up to the transmission line, and it was clean as a whistle. And by being able to do that in a matter of a few minutes, you saved somebody going up there and physically checking all that transmission line to see what they had. And as expensive as steeplejacks are, it definitely proved its worth. So, where's this fit in the ham shack? Well, in my case, it's a pretty good example. Right now, I'm in a restricted neighborhood. My shack is on the second floor of the house. I have a piece of RG8 that goes back to the back property line, and I have a wire vertical up in a tree. And I needed to know the actual length going out there so that I could read impedances at the shack and know what I had at the antenna. Right? So I took a short piece of the coax that I used, got an accurate speed, velocity pattern calibration, which I'll explain, hooked this thing up, shot it out there, read the distance right off the screen. So really made it handy. If you have a tower, or if you have dipoles up in the trees, you can hook a time domain reflectometer up in your shack, look all the way out through the transmission line, and know what you're supposed to see at the antenna. You can instantly tell if your transmission line's in good shape or not. If you have multiple coax switches in line, and connectors, tuners, all that sort of stuff. If you've got problems, you don't know what's going on, literally hook the TDR up at your rig, and you will be able to see every little anomaly. You'll be able to see the switches in the tuner, the coax switches. If there's a failure anywhere, it'll tell you, literally in some cases to the inch, where the failure is. You just measure it out, track it out, and there you go. I shot a staple to a piece of TV cable once, and just for fun, I actually measured it, and the TDR put me within a centimeter of where the staple was. Couldn't ask for better than that. They've gotten so inexpensive. This unit was probably most of $10,000 when it was built back in the 70s, but Like I say, $175, $250 is probably reasonable. And Thomas and I were talking on the way out here. There are other units. You can buy a handheld LCD time domain reflectometer. Does very similar situation, extremely handy in New Hampshire. And that's a place where you don't have I wouldn't put the caveat on it that I would on a digital scope. You pretty well know what you're looking for, and the handheld devices are nice. Frank, doesn't the SARC have a TDR function? Oh, Frank took off. That's right. Did you see that little SARC he's got, Thomas? Doesn't it have one?
I think it does.
Yeah. For y'all haven't seen it, Frank's got a little handheld device, as we always said, about big as a pack of non-filter cameras, that has oscilloscope, network analyzer, all these functions in it, and I believe it has a time domain reflectometer function as well. Extremely useful, and $200-300, brand new. Does anybody have a question about that?
Talk about, tell about what happens when water gets in the cable and what TDR.
Excellent. That's another thing that you'd look for. If water gets in a cable, what's going to happen is the impedance is going to shift. But once again, like we looked for a characteristic signature of a waveform on a scope, and you kind of learn what to expect and how to interpret that. On a time domain reflectometer, there are characteristic signatures. If you've got water in a piece of cable, what's probably going to happen is you're going to look out here, and instead of seeing a flat line where the impedance is constant, you're going to see that impedance drop, and it'll usually slope in a jagged manner, in an irregular manner, as it increases. And when you see that, you're thinking, oh, okay, what's happened over a long distance in my transmission line, and water ingress is the normal thing. If you look out there, this is supposed to be connected to your antenna. Back up. If you're used to looking out there and seeing, and part of it is experiential. If you're used to looking out there and seeing just a little anomaly where your antenna is, and you look one day and you see that, but it's not as far out there as it should be, then that says, okay, somebody's cut your line, the tree's falling on it, pulling it in two. You've got a problem at that point, and it will tell you in feet or inches or ever how you've got it calibrated, how far out there to look. Thomas and I have a project we're going to attack at our church in the next couple of days. One of the contractors cut, this is just another use, one of the contractors cut wiring between two light poles. So we've lost power to part of the parking lot lights. Well, there's a similar device that Tektronix actually built, same size, same type, for the old Bell system that was for looking down telephone wire pairs. This is a model 1502, it's a model 1503. Instead of using a very fast step pulse like this one does with high resolution, it uses a half a sine wave. And it does that because that'll go down a lot worse lines like twisted pairs, Romex, all that sort of stuff, whereas the step pulse would. So what we're going to do is hook that 1503 up where one of the poles is, and look down that buried Romex in the conduit. Once we calibrate, we should be able to see where the fault is. So that's the whole thing. A lot of devices these days are moving to what's called frequency domain reflectometry, and it can do some of the same stuff that was promoted by Ritsu and Hewlett-Packard, primarily because Tektronix held all the patents on time domain reflectometry and the fact that a TDR unit is more expensive in precision to build. But that's another angle as well, and some even use that to generate a TDR display, and that works well too. Does anybody have any questions? Great. All right. Let me show you another interesting variation on a scope, then we're going to look at a spectrum analyzer. Let's see. This is an interesting little guy here for portal operation. It's a 314. Does not have internal batteries. Will run off of external DC or AC. It's dual trace, and it is storage. And that's what I want to show. I was going to bring a storage mainframe, but I literally ran out of space. Let's see. This little guy has been really handy for field service work. You've got a cover that fits over the front, probe pouch. Like I said, you can run it off external DC if you don't have AC, and they're reasonable. I think I paid $100 on eBay for this one, and it was basically functional when I got it. So when you start her up, it looks like a conventional oscilloscope, but where this little guy will shine is if you're down here looking at an extremely slow waveform, some time device that's very slow, you can switch over to storage mode. Switch over to, let's see, single sweep. And I'm going to erase the display. And I'm going to kick a single sweep across. Let's see here. There it is. There's my reset. Switch it. See, every time it writes across the screen, the trace remains. So that if you've got a single shot phenomenon that you want to catch, then you can set it for single sweep, set it to trigger, and when your waveform happens, it'll write one trace, and you can look at it for as long as you want to, photograph it, run another trace up the screen, compare it, all that sort of stuff. This is called analog CRT storage. Quickly, the way it works is there's a grid behind the phosphor. It's called the storage grid. And the beam actually writes a charge to that grid, and it allows flood gun electrons to reach the screen. That's the way it works. This is what we referred to last time. A fellow named Bob Anderson that worked at Tektronix invented the concept. First put it into production in 1963, and that's the way an analog storage scope works. Extremely handy. And let's see. So that's pretty well what that is. It's extremely useful. I know at our church, once again, we were working on electronic drum triggers. By definition, when you hit the drum once, you only get one pulse. So I used this scope to catch the trigger coming off the drum, and was able to find the bad trigger that way. So I've also used storage for looking at clock ticks, that sort of thing, any very slow phenomenon. So you might have a question.
Is that what you repaired your parents' grandfather
Yes.
clock with? You
Yes.
that?
It was one just about like this, and the same sort of thing. When I swept it across and I saw those ticks and I saw the anomaly, it stuck out like a sore thumb. I'd have never heard it otherwise. But that's what storage is good for. Extremely handy. And that's one thing that digital scopes do very well is they pretty well all of them will do storage. It's just got to be within the capability of the unit so that you know for sure what you're seeing. But just right, that was the one I did the clock with.
You told us about that the first
Yeah.
time. Yeah.
Does anybody have a question about this? I want to move to spectrum analyzer. Let's see.
What's the bandwidth that will set?
This little guy is 10 megahertz. Dual trace, 10 megahertz. they make a whole series of the 300s. There's a non-storage one that's the same size, that's 35 megahertz, dual trace. There's 2 or 3 others, I don't remember what their bandwidth is. Oh, there's a single trace that has a digital multimeter built in with LEDs. It's a 305. But they're fun little instruments. Now, one of the more interesting ones is a spectrum analyzer. Let me get it set up.
What is the bandwidth of that schedule? What is that? What's the frequency of that?
It goes from 10 megahertz to 40 gigs.
40 gigs.
40 gigs. And you got to think, too, this was designed in probably 1968 or 69. They were stretching technology back then. But you can see, every once in a while, you'll notice that this signal right here, and this is amplitude going up versus frequency going to the right. So it's not a case of amplitude versus time or amplitude versus distance. It's amplitude versus frequency, but it's still a graph. Now, what you're seeing, every once in a while, you see the signal gets narrower instantaneously. Well, that's when it goes largely quiet. Since FM actually deviates the center frequency, plus or minus 75 kilohertz, you're seeing repeated quick sweeps showing the center frequency being all over the place within that bandwidth. All right, that's what an FM station looks like. Now, I can't think of anything AM above 10 I'd probably be able to see in here. Can you?
No, not without wires.
Yeah, but an AM signal, you'd basically see the center frequency carrier, and you'd see your sidebands either going up in frequency or down in frequency. Let's see. Now, I'm going to back this off a bit. Now, what I've done is I've just what they call reduced the dispersion, and that's kind of old language for megahertz per division horizontally, that sort of thing. I had to stop and think about how to put it. Tektronix coined a lot of these terms, and whereas the amplitude is still measured in dB or voltage or whatever, the horizontal axis is frequency. And what they say is, if this is, say, 1 megahertz per division horizontal, then they say the dispersion is 1 megahertz per division. Old term, you don't see it on the modern digital analyzers. But the long and short of it is, what you're seeing right there is basically the whole FM broadcast band, and each one of those little spikes going up is a signal. Now, an interesting facet of the old analog spectrum analyzers is this hash right here is false. It's not actually there. As you can see, I run the frequency up and down, and I see the stations actually move. But those are spurious signals that are being generated because some strong interfering signal is mixing with the real signals. That's part of the art of using an old analog spectrum analyzer. You learn from looking at the display what's real and what's not, and you tune your head up to ignore what you know is false. You don't have to do that with a modern digital analyzer.
What kind of dip in it?
Say again?
Is that what kind of dip in it?
I couldn't hear you.
Is that what kind of dip in?
No, it doesn't.
There's no way to internally count.
There is, let's see, this one doesn't have it. Some of them actually have. The plug-in spectrum analyzers that go in these mainframes have a 50 megahertz calibrator signal that's available from the front panel. This is really the first model, and it's old and it does not. You'd need an external standard to count from. And the frequency accuracy is another difference. You can, take an HP 4402 or something like that. You've got razor sharp accuracy. You can read the accuracy of the center frequency of a broadcast station on the analyzer, and you don't get that in the old analogs. You get almost accuracy like an oscilloscope, a percentage of display and that sort of stuff. So I didn't have any trouble finding the broadcast band, but I wouldn't be able to look and say, absolutely, this is exactly that station. I'd have to know what I was looking for, or use an external signal generator as a cal standard. So whereas the analog oscilloscopes to me have the advantage over the digital units, the digital spectrum analyzers have a lot of advantages over the analog ones. The one nice thing about the old analog units is they sweep quickly. You get a nice fluid display if you're tuning cans, for instance, on a repeater. If you're tuning IFs in a receiver and using the spectrum analyzer. It's nice and handy for that, but for most uses, the digital units do have benefits over the analog ones. I want to see if I can see.
That unit does not have tracking generator.
No, it does not. Now don't, like the 4402 HP, they all have tracking generators built in.
It is an option, but 4443 kind of has one.
Yeah, and that's another nice thing.
But you could get an external tracking generator for that.
Oh yeah, yeah. There's about 4 that Tektronix made that are external tracking generators that will let you do transmission measurements with these. They're hard to find. I've been looking for some of them for a long time. Now I'll show you an interesting sidelight. You notice when I turn the intensity suddenly down, you see there's a yellow afterglow to the trace. That's a very old, very rare phosphor on the tube. It's called a P2, and it was put on a few oscilloscopes, a few spectrum analyzers back in the 60s and 50s. The goal was, if you didn't have storage, you could turn the lights out, and you can actually see that trace image for almost 90 seconds. You know what I'm talking about. And the trade-off was the phosphors are very susceptible to burns, so you have to be very careful and not run any more intensity than you have to. But I felt like this was an act of God when I got one of these units, and then to realize it had a P7 phosphor in it. So anyway, just a sidelight. But as you dial, basically you've got a frequency dial here. That's the center frequency, and all the ranges are the different bands you can choose. So as I tune to the right and go up in frequency, I've scrolled off past the FM band. Let's see, I'm basically looking at 2 meters now. I don't see any activity that I can see on this little bitty antenna. Let's see. Shift the IF and move that stuff out of the way. Let's see. Might be able to see one of the television stations. No, I'm not getting anything. Yeah, there's one. Let's see. Just barely see it. This extra grass that you see moving left and right as I move, that's one of the TV stations broadcasting digital. That's very weak, but that's what that looks like. And now, does anybody have a question about the spectrum analyzer? I brought this here just to illustrate a different type of special purpose oscilloscope than anything else. If you're so inclined, if you're interested in test and measurement and want to find one, it's a nice accessory for a ham shack, because if you're looking at signal purity, you calibrate your fundamental frequency here, then literally as you sweep up, you'd see your second harmonic, third, and the display is calibrated directly in decibels, so you could read directly what your harmonic content is. That's what the spectrum analyzer is. Anybody have a question? Yes, sir.
Yeah, about how much, of course that's used, but how much do they run?
You know, just like a lot of other stuff, less than they did. Thomas said accurately, I bought this one at the Ham Fest several years ago, and I paid $270 for it. I saw one go for $250 on eBay a week or two ago. There's one on eBay now for $850, I think.
Have you had any problems before? I've never shot for anything on eBay. Have you ever had any problems, because once you get it?
What I do, and I have bought a lot of my test gear off of eBay because that's where it was available. What I found is I look for good photographs. If the photographs are good, if I can see the instrument well, if the description is clear, I like to see I like to see 98.5% positive feedback or better. 99 or better is even better. If they say functional, most of the time the description will tell you a good bit about the instrument. The biggest problem I have on eBay is shipping. If I, just like any of this stuff, I bought this instrument off of eBay, and I had an idea it was going to be a good one, so I literally just all but begged the fellow to let me send him extra money and to pack it like there's no tomorrow. That's the dominant problem I found with eBayers is they don't know how to pack it. It's like their brains turn to mush when they sell something. And I mean, literally, my nicest portable storage scope is similar to this, a little bit bigger. The guy that shipped it dropped it in an old dish barrel like he had moved with, face down, stuffed some cardboard around it and shipped it out. I had to replace broken knobs, bent shafts, all this kind of stuff. The bail was bent up, but it wound up being a really nice instrument. But when it started out, it didn't have all that wrong with it. But no, eBay is a great place to look. I got a dear friend that bought a 491 just like this off of eBay. I think he paid several $100s from his, but it was mint. I'll tell you, interestingly enough, the only chronic problem these units have, the power switch. That hits a shaft that goes all the way back here straight. And there's a big nylon flipper on it that flips the toggle switch up and down. And the nylon cracks and comes loose. So, a piece of scrap dealer in about 15 minutes on a lathe, and she's back in business. But you'll see in a good number of those, they'll say, all works except the power switch. Now, this was a whole series too. The 491 was the first. The 492, Thomas, you help me. The 492 was partially computerized, wasn't it? The next
492 spectrum analyzer?
Yeah.
I don't have a whole lot of experience with it.
Yeah. There was a 492 that was partially microprocessor controlled. The 494.
Yes, it was. Yes,
Yeah.
because we got more.
And the 494 and the 496 were all entirely microprocessor controlled digital units, extremely accurate and extremely nice.
Very versatile.
Yeah, same basic form factor. Hewlett Packard, imagine the 4400 series spectrum analyzers, excellent digital units. If you find any of that, some of the early ones are nice too. Does anybody have a question about the spec analyzer?
Glad we don't mind now.
Good deal. Thank y'all for.
Oh, did you bring the test?
What test?
Test we're going to give everybody.
I forgot the test.